Hello everyone, this is allLogarithmsWereCreatedEqual, and a bit of an extension video of my series on modular arithmetic and algebraic number theory, called Modulo. So last time we discussed quadratic reciprocity, one of the most elegant patterns in mathematics, but one thing you'll find is that there is always more to learn in these branches. Solving one problem often opens the door for more problems. So after we study when there are perfect squares modulo n, the next natural question is when are there perfect cubes modulo n? So this is the story of cubic reciprocity. So this turns out to be a somewhat elaborate topic. I have found a few very good sources for cubic reciprocity, and there are just so many details that you can research and look up about them. I'll put those sources in the description, of course, but before I show you the development of just the sort of including formulas for cubic reciprocity, I must tell you about a wonderful set of numbers called the Eisenstein Integers. So this is sort of intrinsically related, I think, to any proper study of cubic reciprocity. And it's this wonderful set called the Eisenstein Integers, okay? So, and this is what we'll be focusing on, in fact. This will form the basis, and I think that might have been a pun right there. No, seriously. It forms the kind of like a foundation for many ideas and many theorems in algebraic number theory, really, which is what we're getting to. Many of the sources that I've found discuss just many different ideas and theorems about Eisenstein integers, all about this, before they even discuss too much of cubic reciprocity. But they are related, don't get me wrong. I mean, they are still, at least in one approach to cubic reciprocity, it's really built on this field. And if any of you have seen my video on roots of unity, you'll know that we can get very interesting complex numbers when we take the nth root of 1. So I recommend you see that video if you haven't already, or at least do a bit of research on roots of unity. But a very good example of this, in fact, is the cubic root of 1. So it's this whole idea of taking x cubed minus 1, and setting that to 0 and getting the roots. So, like I mentioned in my roots of unity video, there are in fact 3 complex roots to this equation, and one of them we consider to be a primitive root of unity, which we can in fact write as the following. So, in complex notation, we can say it is equal to negative 1 half, plus I root 3 over 2 is this number. And this number will become very important the more we go on in this video. So it's often represented, you'll see it often represented as a lowercase omega. The Greek letter omega is how we're sort of defining it. That's how you'll see it represented. Or, of course, you might also see it represented, sometimes, as its exponential form, or at least I call it its exponential form, where basically we know this is equal to e to the 2i pi over 3. I've also created a video series on why this is true, basically. Why e to the I theta is equal to cosine theta plus I sine theta. And that's basically the whole explanation for this. There are different proofs of that, many of which happen to use calculus, but, I encourage you to study that if you haven't already. But basically, the Eisenstein integers, they are, by definition, all numbers of the form a plus b times omega, where a and b are both integers. Now, this is a bit of mathematical notation. So if you haven't seen it already, it's just saying that a and b are members of the set of integers. So a and b are both integers. And so, as I hope to describe later on, the Eisenstein integers actually form a subset of a specific quadratic field extension, one of my personal favorite topics in algebraic number theory. And so we can represent this, in terms of notation, we could represent this with z of the square root of 3. Now, technically, it's not precisely that, because we have this over 2 involved. So I guess really what we're actually considering is z of omega is actually probably a more accurate way of giving the notation for the Eisenstein integers, because of course omega has this over 2 involved. So technically we are including numbers like 1/2. I guess we could also include 1 plus I root 3 over 2. Or something like that, you know. So we can have some integer over 2, even if it's an odd integer. That is technically allowed in the Eisenstein integers, to my understanding. This is important for a variety of reasons, but most immediately we can consider something called the norm of any arbitrary number in this field that we call the set or field of Eisenstein integers. So how I might denote that in the future is something like n of z being defined to be the norm of any Eisenstein integer. And for any number in a general ring, or what we call a general ring in mathematics, which is a very special algebraic structure of which the Eisenstein integers are an example, this norm function is usually, but not always, but for many of these types of rings, it's defined to be a squared minus the quantity of d times b squared, where d is the value, basically, of, well, basically the radicand of basically the other number by which we're extending the integers. So if you look here, you know, in this case, it's really the radicand here. You know, we could invent other systems, or sort of, you know, design or construct other rings. For instance, z of the square root of 2 would be a pretty good example, where basically everything is of the form, or every element is of the form a plus b square root 2. Or, you know, we can also have z of the square root of 5, where every element of that ring is of the form a plus b root 5, where, of course, a and b are integers. So these are, you know, these are just some common examples of different kinds of rings that we can construct by, you know, adding basically an idea of this new object that is the square root of some number. Very often a prime number is actually what it is. And that's very interesting. Actually, I have a correction first, believe it or not. Where I wrote here that for the Eisenstein integers, this is the norm function. This is actually incorrect. So I'm sorry about that. I'm about to go into more depth into the Eisenstein integers. I might do it in a separate video or something, but ultimately, the final expression for the norm of any Eisenstein integer turns out to be a squared minus ab plus b squared. So, what can we do from here? We can prove that. And before we move on, let me just give you a graphical representation of what this is. So you can see this is, well, I printed this out actually from my Roots of Unity video. And these are the 12th Roots of Unity, all 12 of them actually, but what we're really focusing on, if it wasn't already obvious, was this one right here, which we call omega, and this one here, which we will see by a couple different names, but it is basically the other root, the cubic root of unity. And of course, obviously, it's this one as well, because 1 cubed equals 1, obviously. So it's these three that kind of form the triangle of cubic roots of unity. I cannot emphasize enough that this omega here, it's very important in pure mathematics, very important in algebraic number theory, and so you, yeah, well, we'll see why. Just as we studied whether a number was prime in our exploration of quadratic reciprocity, we will also need to study whether a number is an Eisenstein prime or an Eisenstein composite number. And in fact, this works a little bit differently than in the ordinary set of integers. There are such things as Eisenstein primes, which will become important, and also Eisenstein composite numbers. There are also some examples of numbers that are prime in the set of integers, but not prime in the set of Eisenstein integers. And a good example of that would be 3, because as it turns out, we can actually write this as, well, within the Eisenstein integers, we can write this as being equal to 2 plus omega times 1 minus omega. These two Eisenstein integers, we take their product, we get 3. So, you know, we normally think of 3 as being prime in this ordinary set of integers, but it turns out it's not prime in the Eisenstein primes. And another example, which I have found, is 7, because as it turns out, we can write this as being equal to 3 plus omega, 2 minus omega. And you can check both of these with relatively basic arithmetic, just by sort of distributing each term, and I guess if you want to think of it as foiling. But anyways, the idea is, we have these new ideas of whether a number is prime or composite in the Eisenstein integers. That's really the main idea here, and of course this whole set is so much more expanded, so much broader than just the ordinary set of integers, because we're actually introducing this new imaginary component. That makes it, in fact, in a sense, it makes it multidimensional. But anyways, we'll get to that later, I suppose. I would also like to discuss what are called the units in Eisenstein integers. These are the 6 numbers. In fact, there are only 6 of them in the Eisenstein integers. So I'll say there are these 6 numbers, which I will list out for you, is plus or minus 1, plus or minus omega, and plus or minus omega squared. I showed you a diagram in the complex plane of the 3 different sort of solutions to x cubed minus 1 equals 0, and in a way that pertains to this. In fact, these are all the numbers in the Eisenstein integers, obviously, for which n of z equals 1. Actually, it turns out that these units can have norm equal to either 1 or negative 1, so it's actually counting plus or minus 1. That's why they're called units, basically. And one can prove that these are the only numbers in the field for which this works. I cannot show you the entire proof right here and now, but I will, as always, leave links in the description to provide the sources that have these proofs. And another interesting idea, which will become important later on, is the idea of associates. And the idea there is that if we have 2 elements in a ring, such as the Eisenstein integers, and z, one of them, is equal to a times u, one of the units, then z and a are associates. And that will become important later on as well, so I just wanted to introduce that definition, because there are theorems we'll get to later on. And perhaps most importantly, just like we made use of the Legendre symbol in quadratic reciprocity, we can in fact design a new symbol for cubic reciprocity. This is called the cubic residue character. There are many important attributes to remember about this notation. For instance, whereas the Legendre symbol returned a value that was a solution to x squared minus 1, specifically we add x equals plus 1 or minus 1. You know, these were basically the values that could possibly be returned by wherever we add p on q in our, you know, previous episodes of this series. The cubic residue character is sort of parallel to this, but it returns a solution to x cubed minus 1 equals 0. So again, just as I mentioned earlier, these numbers, 1, omega, and omega squared, in this series, will sort of be our kind of foundation, really. They'll be the most important numbers, because of course they satisfy this equation, well, specifically the positive values, 1, omega, and omega squared. So with all these definitions in place, I will leave you, since I'm pretty much out of time for this video. But I hope to continue this in another episode, so please be on the lookout.